Okay, so how many of you have ever heard of recursion schemes or have done any work with recursion schemes? Oh yeah, that's a lot of people. Who here have done work with recursion schemes or familiar have? Cool, great. Okay, in this workshop we will look at mostly how to use them. This is why this is using recursion schemes. We have a very concrete goal. We are going to look at a lot of exercises. A lot of very small exercises that are that are meant to show what recursion schemes is, how to work with it, the types involved, and how to deal with them, and how to read the types, and write a function that actually type checks and will do what you want it to do. So let me first introduce myself, since some people just joined us. I am Juan Pablo. I work for LambdaConf. I joined them maybe a year ago, and I joined, and I realized that most of their code base relies a lot on recursion schemes. In the main product is actually a compiler, so we use in recursion schemes to handle a lot of the complexity there. It works very well. I like it very much, and it has the benefit that as long as you code type checks, it's very likely to do what you think it does, what you expect it to do, which is rather cool. In this workshop, we will take, rather than I could say a denotational approach, we will use more of an operational approach to working with this. I won't try to explain in the theory behind these things. I'm not familiar enough with it to do it, but I can teach you how to use it and how to take advantage of the library. For this specific workshop, we will be using Scala and the Matreoshka library. And in the presentation, the workshop itself will start with a presentation from me. I will tell you some basic theory about recursion schemes, some basic, so you can understand it. And after that, we will do, as I said, a ton of small exercises, so you can find patterns in between them and find understanding in that. This is the method I used when I joined LambdaConf and needed to learn recursion schemes really quickly to get productive really quickly as well. And I think it's a really powerful way to use pretty much any library with strong types. Okay, so first of all, when to use in recursion schemes? Well, like recursion schemes are for, well, recursion when dealing with recursive structures in general. Whenever you are using in recursion schemes, you are also dealing with some recursive structure. It may be a list, for instance, a const list, the common const list. But it follows the same principles as recursion that a lot of people here are probably familiar with. Who here has used recursion before, like in general, like recursion without recursion schemes? Yeah, that's a lot of people. Yeah. When you use recursion, I'm sure that you may have that you may know something about it. When I was here last year, I went to all recursion schemes talks because I wanted to learn more about it. And there was one thing that was missing that I found it hard to understand, and how to match my understanding of recursion with recursion schemes. Can someone tell me what's their understanding of recursion? Like how recursion works, like how a typical recursive algorithm works in general? The function called itself, yes, that's...
Like some computation is done so that when the next time the function called itself is on a strictly like smaller domain, basically.
Yes. One thing that is very that is interesting about recursion, well, not is that there's often a base case and an inductive case when you're dealing with recursion. You are working often with a recursive structure, say a tree, say a list, and you need to deal with two different cases. You need to deal with the base case, which is where the recursion starts or ends. That it depends on how your recursive algorithm works, and a recursive step. That's the understanding I got when I got my when I got my bachelor in computer science. And one thing I wanted to do when I was here last year was to match this understanding of base case and inductive case, or base case and recursive case, with recursion schemes, like how those two map. And I really didn't find much of a satisfactory answer. So I'm trying to give it to you now. I want you to match your current understanding of recursion, of what you know about recursion right now, and recursion schemes. Okay, so you are probably familiar with the zygoisomorphic apomorphism and that joke that is an inside joke because it's a ridiculous name. And recursion schemes have the popularity of having some ridiculous hard sounding names, so like hylomorphism or futomorphism or histomorphism or zygoisomorphic prepomorphism. Those names were used in the past in the literature, but right now they are mostly not used anymore. We have found some more structure to what recursion schemes are, so we no longer deal with those names. Especially in the ones that are an unfold at a fold, for example, the chronomorphism, for instance, like those names are no longer used anymore. They are historical. If you look at some of the newer libraries on recursion schemes, for instance, Turtle in Scala, I think that has not been released yet, but it may be on GitHub. Or theÄ, which is from Greg File in Haskell, who is the one who is the person who authored a large part of Matreoshka, which is the library that we will use. All of those weird names and stuff are usually put in a SU module of their library because, yeah, they are cool. People are familiar with it, but they are no longer what people used to refer to them. So the names are ridiculous. They are often confusing, but thankfully they are no longer very relevant. So that. Okay. So as I said in the beginning, we are going to take here a more operational approach rather than a denotational approach. We will not talk too much about the theory behind this. I'm sure there's a lot of theory that is very interesting and probably gives a lot of insights, but that's not something I'm very familiar with. We're going to take a little bit more of an operational approach on how to use the library. So for each recursion scheme, we will go into Matreoshka. We will look at the types. We will expand type synonyms. We will expand type families. I call it type families. There are no type families in Scala. There are path-dependent types. But we will expand type functions, and we will extract knowledge from the types. One thing that you need to know about this, which is what the type families are for here, which is like type functions, which is take one type and you will give you another type, is that recursive types have pattern functors. Just keep that in mind. A recursive type is a tree, for instance, and the tree has a pattern functor. A free monad on top of some functor is a recursive structure, and that also has a pattern functor. Not all recursive structures have pattern functors, but the one that we will see in this talk all have pattern functors. There are some cases which you have a recursive structure that doesn't really have a pattern functor. I'm not familiar with those, but I know that they exist. Those will not be covered here. So, okay. As I said, we are going to work with Matreoshka. Matreoshka is a library that was developed at SlamData for Quasar. It started as a modeling Quasar, like a util in Quasar. Quasar is one of the projects that does most of the heavy lifting in SlamData product of the backend side, of course, like the heavy lifting of the backend side. And it was eventually structured into a library, and its name is Matryoshka. Okay, so the first thing that we are going to do for recursion is that we are going to abstract our recursion. We're going to decouple our data, what gives shape to our recursive structure from the recursion itself. How are we going to do this? We're going to make the recursive position polymorphic. So wait, what is a recursive position first? Does anyone know what's a recursive position in an AST? So has someone heard of that? Well, we will talk about it. We will have a lot of examples first. Yeah, go ahead.
Is it like a type parameter, like with cofree, for example? Wow,
Kind of like, yeah, like passing in the functor to cofree to make. No, that's not a recursive position. In a recursive position.
Is this like what determines whether it's a tail calling, tail recursion?
No. A recursive position is a place in the AST that can contain any other node in the AST. That's what makes that AST recursive. Like inside a function in any language, usually you can call another function inside that, and inside that you can call yet another function. Those are recursive positions. They are places in the AST where you can where you can put the same structure itself again. That's what makes this structure actually recursive. We are going to abstract over that. We are going to create a functor that takes the that will map over all recursive positions in our AST. So we will have instances for functor, for foldable, for traversable. Who here is familiar with functors? Great. Can someone give me an example of a functor, or just to have a general understanding of your understanding? Sorry.
Example or definition.
An example of that could just put. Yeah, like you can have a functor on maybe that leaves functions to work on maybe. Yeah, you can have functors on lists. In here we will have functors over recursive positions. Like if you have a functor of maybe, you map over just over the argument of just. In here we will map over the recursive positions in the AST. Just like if you map over a maybe, you map over the just there, or over the sum if you're using Scala C or cats, and you modify that in the just. In here we will modify the recursive positions of the AST. So each time you want to use recursion schemes, you will write a pattern functor. This pattern functor will be a functor over the recursive positions of the AST. We will see this. This is a very rough explanation. We will see examples of these later. I will take maybe 15 minutes more explaining this. and after that we will jump right into the code. So before I go on, I would like you to clone the repository. Let me. Let's go here. Oh, no, this is not the one. I will give you the... This is not a repo I opened. I opened it by mistake. Please clone this repo. It's jsantos17, which is my username, CRS. And there are some instructions here. You should follow these instructions. The only requirement for this is that you have SVT. If you're familiar with the Scala, you probably have SVT installed. If you have worked with it, this may take a few minutes to compile. So I will talk over this, and hopefully, when I finish talking, everything will be compiled. You just need to follow the instructions in the README. I have tested these instructions in a VM, in a clean VM, so it's very likely that it will work for everyone. Let me know if they don't.
I'm having trouble reading that.
Oh.
Yeah, what is the repo?
This is the repo. Can you read it now? Or maybe I can zoom it in. Yep. Right there.
Put the link in Getter if you guys want to download it.
Yeah.
Oh, great. Thank you. Everyone got it? Okay, we'll move from this and back to this. Okay, great. Okay, so one other thing that you need to know about when working with recursion schemes are that you are working with two types. They are related by a type function or a type family if it's Haskell, or a path-dependent type if it's Scala. You will have a pattern functor and a recursive structure. In the pattern functor, it describes what the recursive structure will look like. As I said, we will look at a lot of examples of this. You don't need to understand it right now. So for now, just clone the repo and get it building. Okay, so here's an example of a list. This is a very common list. The list, it's a cons list. How many of you have seen this before? A list that is defined recursively. This is the common, like the definition of a list. You have a list. In this case, a single abstract class, because that's Scala, and we emulate types we emulate some types with subtyping. So you basically have two constructors. You can either be at the end of the list, or you can be an element in the list followed by another element. This is recursive because the next element is a list itself. Like here is a list, so one of the constructors refer to the list itself. In our case, we are going to refactor this a little bit just to make that recursive position. In this case, the recursive position is next. This is what I mean by a recursive position. We're going to make it polymorphic. Why polymorphic? Because we are going to put different things here in depending on what recursion scheme we are going to use. We may put an integer here if we are folding to an integer. We may put a string here if we are folding to a string. So we need to make this polymorphic. And we need, and this allows us to abstract over the recursion. So as you can see here, I have put a suffix here is list f. for pattern functors. Pattern functors like end with f usually, and same with the constructor nilf and consf, and the recursive structure itself usually that doesn't have the f. Just to recap, you can see that the recursive position here, which is next list, has been replaced with a polymorphic argument, here a. This is something that will be done all the time when working with recursion schemes, always. And there's something very interesting here that is very important, is that we have a constructor that has that have no recursive positions. That there are no recursive that there are no positions that are recursive in this constructor. It's nil. This is very important, and this is where recursion schemes where recursion schemes start working. In here, you see there are no recursive like positions. This is very important. Take into account that, and when you look at a pattern functor, when I show you a more complex pattern functor, I want you to look for the constructors that have no recursive positions, because those are where the recursion scheme will start working. We will start recursing, I guess. Yeah, and also note that the refactor, like moving, like making the recursive imposition polymorphic, didn't change anything in this constructor because there's no recursive positions here. I really want to stress this because it's really important, and this is where our understanding of recursion schemes will come from. Go ahead.
So in the list of objects, right? So you have defined the concept. You made it polymorphic, right?
Yeah.
So it should be A, right? So instead of E colon.
Sorry, where?
It should be A, right? Something E colon A, but you made it as E colon in the
Oh, here? Oh, no. Okay, this is something that I should explain to. In this case, this is not a generic list. This is not a list that can have any type in it. This is specifically a list of integers. Why a list of integers? Because doing it otherwise, like making it a list of a generic type of a parametric list, complicates stuff a bit, and it's besides the point, and will only make it hard to understand this. In this case, we will only work with lists of integers, just to make it simple, and help our understanding. We will limit ourselves to a list of integers. Of course, this can be generalized to a list of anything. So yeah, this is okay. It's fine that this int. It shouldn't be A, because we are just working with a list of integers. If we had if we were going to use a polymorphic list that can contain anything inside it, what we would have could be two parameters here, and we would have to define two different functors, one for the list, one taking into account the elements of the list, and one taking into account the recursive position of the list, and that makes things a little complicated. So I have decided to not do that and just stick with a monomorphic list of integers, which will make it easier to understand and explain. So yeah, this is not a generic list, this is a list of integers. Thank you very much for that question. Okay, so let's build some intuition first. This is something that when I'm reading a math book and there are a lot of definitions, I always look for the phrase where the author says, let's build some intuition first, of let's unpack this. Those are like the words I really like to read in a math book, or in a programming book. Like, I always like it when authors try to help you build intuition on what we're going to do. So I'm attempting to do that here. There will be some things that you will need to memorize. That will be, well, you can use it as a reference, but it's very, very useful to know this from memory. These are just some type synonyms in Scala. For now, you should probably know both, since we are going to use both. But for now, you can stick with the second one, which is the simplest one. For those who are not familiar with Scala, this is a type synonym which takes two types. One type here, which is a type constructor, and one type here, which is a concrete type. This type is not an actual type. Like, you need to pass it a type for it to become an actual type. And as you can see here, we will use that. We will take f and we will pass a to it, and so it will be a function from fa to a. In this one, it's somewhat similar. We have w, we have f, and we have a. We have wa, f, w, a to a. Just focus on the second one for now. We will use the first one, but just at the very end. So it's not that important. Yeah, sure.
I'm just curious what the G and G algebra means.
The G algebra is generalized algebra.
Oh, generalized, okay.
Yeah, it's a generalized algebra because it has the W in it. Later, this W will be a comonad. Don't be scared by the word comonad. It sounds scary, but the comonads that we use here in recursion schemes and Corecursion schemes are very, very simple. In this talk, the only comonad that we will use will be a tuple. So if you're familiar with tuples, that's all you need to know about comonads. Like, there's a comonad instance for tuples, for a tuple in constructor, for a two tuple in constructor. But you don't need to know anything else about comonads. I will explain how the comonad, you don't actually even need to know how the comonad instance works for tuples. That's handled entirely by Matreoshka. If you want to understand how it works under the hood, you will probably want to know how the comonad instance works. But for now, you don't need to worry about it. You just know it's a comonad, it's a type constructor, and that's it. In our case, it will always be a tuple constructor. Nothing else. No, it's nothing more complicated than that. Okay. Here I'm going to show you the method that we're going to follow to understand each recursion scheme here. This was taken from Matreoshka, and these are the types in Matreoshka. We don't even need to look at the implementation. We are just going to look at the types. In implementation, we'll mostly is something you can look at if you want, but in my experience, it's not really necessary. In the types, provide enough information for you to be able to get what you need. Okay, so Matreoshka has this method, kata, which is a katamorphism, and it takes some arguments. It takes a t of type t. I will tell you later what it is. It takes an algebra and produces some A. We just need to look at the types, and we will figure out how to use this. Okay, so the first thing that we will do is expand the type synonyms. As I said in the beginning, we have an algebra, which is the type synonym that I showed you in before, which is FA to A. So we have this algebra base A, the name's base. Instead of F, it's called base. Oh, okay. it will be go from base A to A, and we will produce an A, okay? And what is T? In our case, T is the recursive structure. In general, we will call the recursive structure T, and the result A in the case of recursion schemes. In Corecursion schemes is different. I will explain it later. So in our case, our recursive structure is T, is a list of these. In this case, this is a polymorphic list in this example. A previous example was an int list. So if we expand the synonyms and make all the types very monomorphic, we can look at what we can look at how this works and how to use it. So here we have a T, in our case will be the recursive structure. This is a concrete type. This is a type. This is not a type constructor. It's just a list B. And so in order to use kata on some T, we need to give it a list, of course. For example, like if you are mapping on a function, you need to give it some structure to map over. And we have an F, which goes from list F be integer to produce an integer. So let's look at this again. Okay, so if I want to, for example, have a list and I want to get the length of that list, how is the length of a list represented? What will be the result of taking the length of a list? Yes, an integer, right? So yes, I want to use kata to get an integer. Okay, so I'm going to take A and I'm going to specialize it to integer. So I'm going to take all A's here after expanding the type in synonyms and replace them with integer. So I take A's and replace them with integer. A, integer, like list F, B, integer, integer, integer. Okay. So in order to get the length of a function, we should be back. Yeah, there it is. Sorry? This A here. Oh, this A here shouldn't be here. Thanks for noticing. It shouldn't be there because it has been made monomorphic. So it should no longer be a type parameter. Thanks for noticing that.
Like just on the last one or on all of them?
After we replace A, like here, okay, A. This is no longer monomorphic. It is no longer polymorphic. So the A shouldn't be here in the last one. So yeah, we take the A, we replace it with integer, and that should be enough to get to give us like an idea on how to write a function to calculate the length. This falls out right out of the types. You don't really need to look at anything else more than that. Well, some logic on how a list usually works. So in order to get an integer out of a list, we need to write a function with this type. From the pattern functor of a list, which is list F be integer to integer. So let's look at the previous slide so we can look at list F again. So we need to go from list F of integer to integer. So we have this list F. We need to handle both cases. We need to handle nil F and we need to handle cons F. We will replace, in this case, the I with integer. This A will be replaced with integer. That's why we made it polymorphic. That's why we refactored our data type to make it polymorphic, because we need to be able to put the integers here instead of lists. Okay, so let's go back to this. So we need to handle both cases. This should be nil F, I just realized it. We need to handle both cases. We need to, so if we get so we start with the non-recursive positions, and that's why I told you that it's very important to notice that the nil constructor doesn't have recursive positions in it, because we are going to go from a list F of integers to integers. Like how do I get first here? Like how? So I want to get integers, but my arguments are integers. That's something I found really confusing when I started with recursion schemes. But then I realized that this makes sense because there are some constructors in our data types that don't have a recursive imposition, so they don't have integer in them. In this case, is nil. So we will start with nil. This is equivalent to the base case of normal recursion. That when you write a normal in recursive algorithm, this is the base case, and this is the recursive case. Like, so when we get to the end of the list, the list is 0, and we get to the next element, we just add 1. So in this case, n will be an integer, so that's why it's polymorphic. So we will look at more examples of this. I find it really useful to look at one example, then another one, and then try to find patterns that are common in all examples. We will do that writing code, so you can play with it and get a feel for the types. Okay, so and this is some very simple code, but gives us some interesting insights on what's going on here. We know that in order to fold a list, we will start with the non-recursive position. We will start with the end of the list. We will go all the way to the end, and which in our case will be nil. If you are not familiar with a cons list, I will try writing one here. So in order to have a cons, so for an example of cons list, we will see this in the code. So don't worry if you are not getting it now. So in order to represent a cons list, you start with cons and say 1 cons 2 nil. Okay, so we have cons 1. This is equivalent to a list of 1 and 2. So when recursion schemes, when Matreoshka is going to take our list, it will go all the way to the end of the list, to the deepest part of the list, in general to the deepest part of the structure, and start folding there. Because this is the place where we don't have a recursive position. So we will go all the way here to nil and replace that with 0. So we have cons, so we will have 0, then 1, 0 plus 1 is 1, plus 1 is 2, so the length of the list is 2. I said we will see a lot of examples of this, so don't be worried about it. And now, how does pattern functors, the list f and list are related? They are related by fixed points. A fixed point is something that takes a pattern functor, say list f, and converts it into list. There are several pattern fixed points that we can use. Here are some common ones. The easiest one is fix. There are some other some other fixed points that give us some more structure. For example, free or cofree. These are, as I will show you later, all of these are fixed in disguise. Is very they are all very, very similar to fix. Yeah, so intuitively, when you get a fixed point converts your pattern functor list f into list. Or if you have an expression f, which is an AST, it converts your expression f into an expression. It converts your non-recursive functor into a recursive structure. You just need to know that, like you give your pattern functor to fix, and fix will get you back a recursive version of it. Let's look at fix. Who here have seen fix before? Okay, so someone can explain me what fix is, what fix does, what is it for? What is the fixed point combinator? This is a fixed point combinator at the type level. You can also have a fixed point combinator at the term level, which I guess is more common in the lambda calculus, but in this case at the type level. Can someone explain to me what the fixed point combinator is?
I think you will try.
Yeah, go ahead, please.
So fix is kind of a structure. So it has defined itself by itself. For example, a professor can be a student, and he has furthermore students. So, for example, professor described by his name and something, and then it's followed by list of professors who can be students, his students also. So, a structure described by its own structure is fixed.
Exactly. Yeah, go ahead.
I would try to, like, by example, like, what did you call it? Recursive positions? So, like, a structure has, like, recursive positions.
Yeah.
And inside the structure, what it would be able to do is, like, take such a structure and be able to place that structure itself in recursive position
Exactly.
at the next level. So, like, the example would be like list. At every point, instead of having an element, you would insert the possibility of having a list there. So you basically make trees of arbitrary. Yeah.
Exactly. So yeah. So with fix, I will pass it a pattern functor. I will pass it a type constructor, f here. Fix is a type combinator. We can say in the Scala is a case class, which takes a type constructor f that is a type that takes a type to create another type, and it will take that f and will pass fix f to it. So it will put f inside itself, but it needs to put something in between them because we need some sort of constructor. So we have an intermediate fix in between the functors. So basically what ff is, what this is doing is putting f inside f. This is all it does. Don't think too hard about this. Fix sometimes gets solved out to be something very mystical, very difficult to like understand. Don't think too much about it. Think of it like I give it a functor, and it will give me a recursive structure back. In my experience, that's the best way to like understand it. It will just take my f and it will pass the recursive structure to it. Like it will pass f to f. Don't think too much in about it. Okay, this is another fixed point. In this case, is the free monad. Free monads were like all the rage, like last year and 2015. I think that they are still very, very popular. But if you look at free, free is pretty much fixed. It's the same thing. Just look at the suspend constructor for free. A free has two constructors. Has a constructor on A and has a constructor suspend. Has a return in constructor and a constructor suspend. If you look at this type here and then compare it to fix, you will see that they are pretty much the same thing, just with a different name. Instead of fix, it's called free. And you have, of course, you also have an extra constructor here. So yeah, free, all it does is pass the functor to itself to make it recursive, and we'll also add a new constructor, A. This will become very useful. We will use free to model unary functions later. We will create an AST that will have that will model a unary function, a function with a single argument, and our single argument will be returned, and the rest of the AST will be held by suspend. So yeah, this is very, very similar. The other fixed point is cofree. If you look at cofree, it's again the same thing. Just that in this case, instead of being a sum type with return and suspend, it's a product type with a head and a tail. If you just look at the tail and compare it to the suspend constructor, It's the same thing, just with different names. Instead of free, is cofree. And with fix, it's the same thing, like fix F. In this case, is S free S, and in this case, is S cofree S. It's the same thing. All of these, in the case of cofree, it also has something else in the as a product type. So we say that cofree models an annotated tree often. We will use that later. We will annotate a tree using cofree. But these are basically the same thing. They are like one is fixed with an extra constructor, that's free. One is fixed together with some value A as a product. But as you can see, it's the same thing. Go ahead.
Just to clarify, so when we were talking about our list, we said it's a monomorphic list and the int is hard-coded. We're not going to make it polymorphic. Here, there's an extra type constructor, but it's still monomorphic, right? The A is the type of the annotation. It's not the type of the data that's held in the data.
Yeah, in this, when we look at cofree as an annotated tree, head A is the type of the annotation. Let's say you have an AST and you want to annotate every node in the abstract syntax tree with its type. We will see an example of this. Don't get scared if you don't understand it just yet. We will see a lot of examples. But yes, head A is the type of the annotation. In the case of free, return SA is the type of the argument that will be passed to our single function argument. As I said, we will see a lot of examples. This table is really important. I have a gist with this. You should probably open this URL, which has this table, which relates pattern functors with the recursive structures. In the case of fix, if you just have fixed list F, the pattern functor of fix, got it. Oh, yeah, sure. Yeah, it's patterns for it too. Was everyone able to copy that? There's a link to a gist that has the exact same table. Oh, this is really important, and that's why I made it into a gist. You will need that as reference when we look at some Matreoshka types. It will be very useful to be able to refer to that list, to that table. So yeah. So we have a fix of list F. This is the recursive instructor. As I said, you give it the pattern functor, you pass it to fix, and it will give you back, like fixed list F, the recursive structure. And as a pattern functor, that will be list F. In the case of free and cofree, their pattern functors are have a bit more structure since one have an extra constructor and the other one has an annotation. There will be a little bit more like in a structure. So if you have a free list F int, its pattern functor will be coemp int list F. Don't pay much attention to coemp or why coemp is it's a comonad. Don't pay much attention to it. Just look at you need to know that free has coemp as a pattern functor, cofree has mt as a pattern functor. We'll look at a lot of examples right about now. So were you able to get the in the examples up and running? Anyone had trouble with examples? Okay, so yeah, go ahead.
Wondering at a high level, what are coemp and MT?
Coemp and MT is the environment comonad. this is the names that Matreoshka use. They are a bit confusing because they are comonads and they sound scary. But you can also think of these as freeF, which is the pattern functor for free, or empty is CofreeÄ. This is the comonad in transformer, the environment comonad in transformer. But that's not relevant right now. You don't need to understand how the environment comonad works to understand this. That's beside the point. It's not necessary. It just happens to be the exact same type. So Matreoshka uses that, and the literature uses that as well. So, but you don't need to understand how the environment comonad works in order to understand this. So don't worry about it. It's just a type. Like the pattern functor for cofree is MT. The pattern functor for free is coin. Okay, so now we will look at examples. Let me change this so I can mirror my display. Can everyone read that? Is that readable for everyone? Should I make it larger? Okay. So now I will open Emacs. In here I have made an effort. Yeah.
Question on the usage of the checkpoints. Do you have tags at the checkpoint?
Yes.
Do they build on each other, or like? So if we check out the checkpoint, we're going to get a detached head, and then are we going to merge in the new?
Yeah. You will get a detached head. Do not merge in the branch on that. Just stay in the detached head. And then you can checkpoint a different checkpoint. You can check out a different checkpoint, and you will get to the next example, which you will be still at the detached head. They're just different commits that and they do build on like each other, because in some places we write a function to show an AST, and after that we will use that show function to show some transformation that we made on the AST. So they do build on each other.
So does checkpoint 2 have all the answers for checkpoint 1?
Exactly. Yeah. They like if you go to checkpoint 12, you will have everything from checkpoint 1 to checkpoint 12. Okay. So now I'm going to open Emacs here. I'm going to check out to checkpoint 00. That will give me a detached head. And I'm going to open Emacs here. Okay, so here we will start with the same linked list that we had at the beginning. Is the text large enough? Look a little small from here. Yeah, sure, most definitely. Is that better? Oh, sorry. Yeah. Okay, so we have again a linked list. I call it linked list instead of list, just to not confuse it with the default Scala list. I call it a linked list. We have linked list F, which is the exact same thing we had in before. Linked list F has an A parameter. We have a constructor that doesn't have recursive positions in it, and we have a constructor that has recursive impositions in it. In this case, int and next A. In order to use recursion schemes, we will need to define a functor instance. This will be a functor instance on linked list F. This is not the usual list functor that will map over a list and take like. This is not the usual map over the list. Instead of mapping over the elements of the list, we will map over the recursive positions of the linked list. So if you see here, the integer called it E, I pattern match on that, this goes unchanged. We don't pattern match on the, we don't apply functions on the elements of the list. We apply functions to the recursive positions of the list, in this case next A, which is the polymorphic position. So F is applied or next. So yeah, as I said, this is not the usual list functor. This is a different functor. This is not a, and this is why I didn't make this polymorphic, because if I did, we would need to define two different functors here, which could be a little confusing. So yes, like the functor instance for the linked list, all it does is map, is take the mapping function and maps that over the recursive positions. It will go from A to B over linked list FA to a linked list FB. This is the regular. This is a functor. It's not a usual functor that we usually use with lists. It's a pattern functor. Let's look at examples down here now. Okay. So the first thing that we're going to do is we're going to write a function. We are going to write an algebra that what it will do is take this list and convert it to a chord. This chord here, this is actually just a string, just pretend it's a string. It's just an efficient string for like appending, so we can append this quickly. Maybe I should have made this a string, but if you see chord, you can assume it that string. It's a way to represent the strings to make it inefficient when we're appending, like we're appending here a lot. So we're going to write an algebra. So let's open also Matreoshka. CXP. We're going to Matreoshka, and we're going to the recursive type class, and we have kata here. I think I show you this here. I think I show you this in a slide. We will take this kata here, and we will expand the type synonyms. What we want to do is we want to get the string. We want to get a chord. We want to take our list and we want to convert it into a string so we can show it in the screen, and we can like display what is inside the list. So let's go ahead to Matreoshka. Let's say kata. Okay, so kata takes a T, takes an F. There's some implicit parameters, which is the functor that we define it, and will produce an A. So let's go ahead and get rid of this A and replace it with chord, which is a string. So we are going to just copy this just to explain it. We are going to change the A to be a chord, which is a string, to be a string. Okay. Now let's go ahead and expand the type synonym from the algebra.
Wait, a string or a chord?
Oh, chord. Yeah, it should be chord. Chord is a string. If you see chord, you can just mentally replace them to be a string. It's the same thing. It's actually a zipper, but this is what Scala uses under the hood to make this efficient. So we replace the A with chord. Now let's expand this type synonym here, this algebra-based chord. Can someone remind me how to expand this? Or tell me how to expand this? This base of chord to chord, yeah. So let's change this. Base of chord to chord. Okay. We know that our recursive structure is a linked list, and the pattern functor of a linked list is the linked list F. So we are going to replace T and base now. So let's take this and copy it again. The T will become linked list. Base will become linked list F. And now we can change this to linked list F. As you can see here, this is asking for an implicit parameter for the functor, which we define it up here, which is exactly the same thing here. Functor linked list F, which is what Matreoshka requires us for us. And we need to write this function here, which is the algebra. So we are going to go ahead and write this algebra. This algebra, I wrote it as an algebra, like algebra linked list F chord. This can also be changed to linked list F chord to chord. Okay, so we need to write a function that goes from linked list F chord to chord. We need to handle both cases here. We need to handle these two cases, the nil F case and the cons F case, and from each of these we need to produce a chord, which is a string. We need to produce a string. I usually use algebras. I denote them with this pretty F here. I don't know what's the name of this character, but I like it, so I use it a lot. So we are going to write this function from linked list F chord to chord. So we have the case of nil F. That's the very end of the list. So we are going to make that into a closing bracket. In the concept of a list, we will take the integer here, do it into a string to convert the integer into a string so we can show it, wrap it into a chord, put a comma there to make it easy to read, and continue with next. In this case, next is linked list F chord. So the recursive position in this case will be a string. You can see that in our previous example, this was an integer. In this case, it's a string. So this is why we made it polymorphic, because we are going to use it with a lot of different types. So we needed to make it polymorphic. However, this has a problem, and we will show, and I will show you in the terminal when we execute this code. Yeah. Yes, exactly. But that's something we can't solve with kata. We will solve it later. You will probably not use recursion schemes for something as simple as this, because that would be overkill, but just as an example. So yeah, in order to show, what we will do is going to do list kata show F. And since there's no starting bracket, I'm going to add 1 here. So now let's go ahead and execute this code. I'm gonna make this much larger. Let's run SVT. If you haven't run it yet, you should probably do it. Just open a terminal at the root of the repository and write SVT on it. And then just execute run. It will compile our code. And just as you said, we have a comma at the very end. Oh, this is a little small. Let's make this larger. Yeah, that's better. Just as you said, we always have a comma at the very end, which is not very nice, but it will do just to show the list now. This will do. Okay, this is our first example. In the approach that I am taking here, I'm going to show you a bunch of very small, different examples, and I want you to be able to look at those examples, find common patterns in between them, and gain understanding from that. So let's go to the next checkpoint. If you get lost at any point, you can just check out in the checkpoint I'm going to check out to. So you don't need to. Yeah, that will give you the touched head 0, 1. Okay. Next example. Okay. Now we are going to sum the elements of the list. This is very similar to what we did for the length and for the show. Again, we are going to we want to produce an integer from a list of integers. If you sum a list of integers, you will get an integer, right? So we will go back to Matreoshka. Let's remove all of this, and we are going first to replace the a. Since we want an integer, we are going to replace this with integer. This also with integer. Now we're going to expand the type synonym and replace base. So let's first replace the type synonym. F base integer to integer and integer at the end. Now let's replace t and base. We know that t is a linked list, is the recursive structure itself. It's a concrete type. It's not a type constructor. Base, it's a type constructor, so this will be linked list f. And the functor will be on base, which is the same functor. We will use the same functor that we used before. Okay, so we need to write a function of this type. So in order to do that, we will write an algebra, like which will do this. So we have sum f. The very end of the list doesn't have a value, and the additive identity here is 0. So we add 0 to anything, we get the same thing. So since the very end doesn't affect the sum, it will be 0. In this case, unlike the length, we are not adding 1 since we're not counting. We are summing the elements, the integers, in this case e. So we will take next and we will sum e to that. And now we are going to do a sum of that, and we are going to pass it a list, and it will return us an int. So basically we will call list, we will call kata on it, and pass the algebra that we just wrote. Let's execute this code. I will show you the code that is executing this. This is in crs.scala. We basically, these are just calls to the to the functions that are defined in the other objects. So let's execute this. Run. Okay, so we have the sum of the list. 1 plus 2 plus 3 is 6. The length of the list is 3. We already went through the length implementation. This is another example. Any questions at all about this? Is it what I want you to see here, which is how I learned recursion schemes, and I think it's a very powerful way to learn this library because there's so much type information that you can take advantage of, is to look at the types, look at the similarities between the types, in between the examples, and try to gain an understanding from that. Okay, so let's go back to linked list. Linked is the algebra that we saw in the slides. Nil f in the very end. If we just have a list of nil, that list is an empty list, so its length 0. If we have some cons, we will add +1. We ignore e. Since we don't care what's the value, we just want the length of the list. Okay, as you can see, these are some very similar examples with others. Show sum. Oh, I accidentally deleted that. Sum, length are all very similar. So let's look at another example that is not as similar as this. Let's go to the next checkpoint. Sum and length lists. Okay, now we are going to write the actual map. This is the usual map for a list. Who here has written map for a list? That's usually recursive, right? This is the exact same thing. Only that we don't need to take care of the recursion ourselves. Matreoshka will do that for us. So we will write an algebra. This will be a higher order function. In this function we'll take a function as an argument, f from int to int, and it will give us an algebra as an output, which will be another function. So this is a function that takes a function and will get us back a different function. So if So if we were going to map over an empty list, what would be the result of mapping over an empty list? It doesn't matter what we map over that empty list, we will always get an empty list, right? Because the list is empty. There's nothing to map over. This is more interesting in the case of concept when we are going to do the list concatenation. We need to look at this algebra a little bit. So let's go to Matreoshka. This example is a little more complicated than the previous one, since we are going to produce a linked list from a linked list. So let's go to Matreoshka again. Recursive, let's delete what we did just now, and start here. You don't need to look at implementation, just look at the types, and 99% of the time you will be fine. Okay, so what is our recursive structure? Who can tell me what's our recursive structure here in order to map over a list? This is the same as the previous example. The recursive structure will be linked list here. The base of the linked list will be linked list F, as always. If you have a linked list, you usually call the pattern functor linked list F. What do we want to produce in order when we have map and we map over that? What do we produce when we map? A list, right? Okay, so let's go ahead and replace this A with list and see where that leads. Linked list. Okay, so we want to produce a linked list. So let's replace the other A with a linked list too. Okay, so we have T's linked list, we have an algebra linked list F, and we want to produce a linked list since the end output of mapping over something. So mapping over a linked list will always get us a linked list. So we want a linked list. So, made that lowercase. So let's expand the type synonym here. Who can tell me how this will be expanded? How this? Sorry. Go ahead. Linked list F. Remember that this is a type constructor, so we need to pass something to this. Linked list F. Linked list to linked list. Okay. Linked list F, linked list to linked list. Okay, and we need a functor, which will be the same functor as before, as all previous examples, in order to produce a linked list. Okay, so we need to write a function of this shape. We need to write a function with this type in order to map over a list. So let's go ahead and try to write that. We have this algebra linked list F. Let's expand the type synonym here. Linked list F, just as we did before. To linked list. Okay. So we need to pattern match on linked list F. We need, again, to handle both cases. We need to handle the case of nil F and the case of cons F. In the case of nil F, if we are mapping over an empty list, what do we get? An empty list, so we get nil F. In the case of cons F, this is more interesting. We have linked list F of linked list. So the recursive position next will be a linked list. And we have the A which is an integer. So in order to go from linked list F to linked list, we do a cons F with fix. We create cons F, apply the function over the element. For example, a function to double the elements of the list. and continue with the rest of the list, which is next. In this case, the recursive position is a linked list. So we saw an example where the recursive position was an integer. We saw an example with the recursive position was a string or a chord. And now we see an example where the recursive position is a linked list. So just to stress the point that that's why we needed to make it polymorphic. So in order to call this function, all we need to do is pass some function to our function to generate the algebra, and then we can call kata on that. And this will be mapping over a list. So let's execute this code.
Why do we need to specify tag for kata?
Wording. Oh, here? Oh, actually we don't. I just added it in case someone wanted to see what type is in there. I can actually delete this, and this will work just fine. Yeah. I just added the type annotation, so just to give more guidance. Okay, so we are seeing a pattern here, where the recursive position becomes the end result. So why does the recursive position becomes the end result? That's because when we're folding a recursive structure, we will start with the leaves. We will start with the part of the structure that are not recursive. In the case of a linked list, that's the very end of the list. In the case of a tree, those are the leaves of the tree. So we first fold the leaves, and then we fold what depends on the leaves, and that's how we can fold the entire structure. We will see another example of lists, and then we will switch to a different structure, to an AST, and we will do some rewrites on the AST. And you will see that doing rewrites on an AST, or on an abstract syntax tree, it's pretty much the same thing that we have done here to write the map function. Only that in this case, we're just modifying programs, which, go ahead.
And the reason you chose cat is because we need to go to the
Yes, we could do this with ANA. For some of the examples, could be done with ANA co-recursively. We will see some examples of that. In order to tag a tree, we will use ANA. But I find in general, at least for me, recursive structures are easier to understand first, and then co-recursive schemes, not structures. Okay, so let's go to the next checkpoint, checkpoint 3. So you can check out. Oh, I have uncommitted changes because I changed that. And now checkpoint 3. Oh. Okay, now we are going to write filter on the list. Who here has written filter for lists? This is the exact same thing. We will do the exact same things, only with recursion schemes in this time. So if we are filtering an empty list, what will be the result of filtering an empty list with any predicate? An empty list, right? It will always be an empty list. Doesn't matter what it is. What if we find a concatenation of the next element? We need to check if the predicate holds. If the predicate holds, we are going to produce a linked list. So we need to fix over the concept constructor. So as I told you, fix, what it does is you give it the pattern functor, in this case the constructor conf, and it will give you back the recursive structure, which is linked list. So we are going to do fix concept in next. If the element is not actually in the list, we are going to we're going to omit the element. We're ignoring it here, and just append the rest of the list. So let's look at how we call this code. just CRS Scala here. Oh, no, not that CRS. This CRS. Okay, so this is an example of mapping. That was what we did before. We map over a list and double every element of the list. The summing, the length, we already saw this executing, and the filter here. We are going to filter this list. In this case, the list is 1 to 3, cons 1, cons 2, cons 3. And we're going to pass it a predicate, which is basically take the modulo of the element and check that it's not 0. And that's how we keep odd numbers in the list. So let's execute this code. And we pass it this list. And we just get the odd elements in the list, 1, 3. Okay, so let's recap in a little bit, just looking at this structure to give you an idea on how this works. So we're representing our list as a cons list. So we have cons of 1, cons 2, cons 3, and nil. So when we are going to get the length of this list, what recursion schemes will do first is replace the leaves. So we are going to get this, and this will be replaced. This will be 0. Since after that, if it finds a cons, it will be 1, and it will sum this. Then it will go to the other. I accidentally changed this to underscore. It will find the cons here, and it will add another plus here. I don't know if I have the parentheses matching correctly, and then it will go to the outer constructor, and it will be 1 plus. So let's see if I have to. So in order to get the length of a list in recursion schemes, we'll start with nil, which is the non-recursive part of this list. It says if we are getting the length nil, the length of nil is 0, so it will replace with 0. There's an element here, so that will replace it with 1. There's another element here that will be replaced with 1 again. There's another element here that will be replaced with 1 again, and we will end up with a list with summing 1 plus 1 plus 1, 3. And this is how all recursion schemes work. We start with the very bottom of our recursive structure and work our way up. And it works the exact same way when we are transforming structures. Okay. Okay, now let's go to the next checkpoint. Yeah, sure, go ahead.
So in checkpoint 3, can you open the filter?
Most definitely.
Probably easy, but don't like that. So it drops new with fixed, it drops the second case 2, but the next stays as max without fixed. I don't quite understand.
Here?
No, sorry.
Here.
Yes. Yeah.
Next here, next in this case, next is the same as the result of the filter. So next will be a linked list. Will be a linked list, which is what goes next after the E here. Well, previous lecture.
Why we need to drop new list?
Why we need to drop what?
New. The first.
Ah, this here?
No. First case, you drop new with fixed, right?
Oh, this fixed nil f? Yes, because nil f is the pattern functor. But I need to produce a linked list, not a linked list f. And And what fix is, if you give it a pattern functor, it will give you back a recursive structure. In this case, the nilf is not recursive, but still it needs to be grabbed in fix because in the definition of fix, fix doesn't care if it's recursive or not. It will still grab a constructor fix even if it's not recursive.
But if you scroll up in your code, you have a nil constructor that is fixed at nil f, so you could just...
Oh yeah, I could definitely use that. I did create some constructor, and this is something that is done very commonly when working with recursion schemes, which is, this is also necessary, by the way, but I added just to clarify. This also could be, instead of doing like this, I could just refactor it out into a function, and instead of doing this, we can do just nil, like this. No problem. And we can do the same with here. Now it comes in next. But this is just a refactor. This is just calling a function up here, right? That does the exact same thing that we were doing before. These are just some helper functions.
Why is filter inverting this parameter compared to map? Map is the first parameter list.
Oh, that's just a mistake on my side. Like it, I don't know. Yeah. Well, okay. What was the question again? I think I misheard it.
Fine.
Oh yeah, we have f here and we have the predicate here. Yeah, it could be either way. It doesn't matter. I should have probably made it symmetrical instead of separate like this. yeah, I understand you. Yeah, but it doesn't matter. In the order of the parameters here doesn't really matter. Well, when we call it, I'm calling it differently, so it won't compile if I. Okay, now, as we said, we had a comma at the very end of the list, and we really can't handle that only with kata, to don't show the comma at the very end. In here I have an example, which I call the smart show, because I couldn't come up with a better name. I'm not very creative. So I just call it smart show, which uses which instead of using kata uses para. Don't think too much about this. This is a bit more complicated. But what para allows us is to look at the next element of the list. So we actually check if the next element of the list is fixed nilf, which is the very end of the list. We don't put the comma. If there's something else here, which is definitely cons, we put the comma. If not, we don't put the comma. And after that, for list, we will use a smart show, which won't show the comma at the very end. As you can see here, I'm pattern matching on fix. I'm not pattern matching on the pattern functor. I'm pattern matching on the recursive structure. And this is why you may have heard that paramorphism works with primitive recursion. Why? Because I have access to the actual recursive structure here. I don't only have access to the pattern functor. If you see all the other examples, they always match on something that ends with f. They never match on fix. So that's why they call paramorphism a recursion scheme with primitive recursion. Primitive because we have access to the recursive structure itself as part of the tuple. Okay, so now that we have seen some examples with lists, we are going to move on and we are going to see examples with a tree. And we are going to look at some nice graphs and pictures which may make it easier for some people who are more visual. So let's go into the next checkpoint, checkpoint 5. Okay. Now on checkpoint 5, you will want to open the expert file. You can see it at the very bottom of my screen here. now we are going to define a different recursive structure. This is no longer a list. This is, in this case, this is a tree. But this works very, very similarly to the list. We will have a polymorphic parameter in our structure that will represent the recursive positions in this structure. In the list, the only recursive imposition was what was the place that told us where's the next element of the list. In the case of a tree, we have more recursive positions. For example, if we want to add f, we have the left-hand side and we have a right-hand side, and both sides, I want them to be able to be anything. So I want to be able to add like the results of a multiplication, and I want to be able to multiply the results of an addition, because that's what usually an AST needs to be able to represent. It needs to be able to represent any program. So now we are going to write a functor instance for this recursive parameter. Once again, it's very important to note that here we have a constructor that is not recursive. Which one is the constructor that is not recursive here? Literal f. And that's where everything starts. That's where the recursion will start. Just like if you were writing a normal in recursive algorithm, you will first handle the leaves and then you will handle the rest of the tree. In this case, we will first handle the literal f and then we will handle any other case. We need to write a functor instance. This functor instance maps over the recursive imposition. So you give it a function from a to b. You give it an exprf for parameter epsilon a function from a to b, and it will give you an exprf of b. In literal, since there is no recursive impositions here, we don't need to do anything. We just pass it and change it. We need a type annotation because the Scala type inference doesn't work very well. So Scala requires me to say this is b, because there are no a's in literal, so there is no way for it to infer that it can be b. So I need to tell it. In this case, L and R are both recursive positions, so we have add f of fl, fr, the same with multiply, the same with subtract. And as we did before, right now we're going to write a function to help us print this. And in order to print this, since writing code to print a tree is kind of labor intensive and takes a while, what I did here was is mapping this structure into a structure that is already in scalaz, which is called a rows tree. Has someone heard of rows trees before? Or multi-way trees? Yeah. We are going to map our function to a multi-way tree, and we are going to use kata to do that. So let me show you the example. We also will we may also need a traverse instance. This is also very, very mechanical. If this was Haskell, I could derive this automatically. Like the compiler could do this, or maybe in cats the kittens library can derive this automatically. So don't think too hard about this. These are very, very, very mechanical ways to write these instances. It basically just goes through every recursive parameters and applies a function. In the case of traverse, you need you need to be able to sequence, so you need a applicative here. But don't think too hard about this. It's not very relevant. What you need to understand best is the functor instance, which maps over all recursive positions in the structure, and allows me to apply a function to every recursive position in the structure. Okay. As we did with the list, we are going to write some helper functions here that help me just call fix on top of the pattern functor. So in order to create a literal, I need to create first a literal f, and then call fix on it, so it will give me back my recursive structure. Same with that. In order to create an add, I need to create a pattern functor, add f, and then fix it to get me back a recursive structure. Same here and same here. Now it's more obvious why I call it a recursive position. Because the type of my expression is expr, which is type expr fix of exprf. And you can see that the result of adding is an expression that can be put in any other places on the expression. And same here is another expression. So this is why I call it a recursive position, because you can put any other part of the structure inside it. So now it's more obvious why I make it polymorphic, right? Or why it's called a recursive position. Okay, so what we're going to do now is try to get some way to show this tree. But first I will show you how to build, how to write one of these trees. We will go to crs.scala. Not at CRS again. dcrs. Oh, nope. And let's load back. Okay, so in order to create a tree, I'm going to create a tree which is expr subtract, multiply, add, literal. Okay, so in order to build a tree, when you write this expression here, you actually think very much like Matreoshka does. You first write the literals, then you write functions on those literals, and then function on those expressions. So I will write this as you would write this in math class. So this is equivalent to, I will start just like Matreoshka does with the very bottom of the tree, which are the leaves. So we are going to do 3 plus 4, which is the add here. And after that, I want to multiply that by the literal 6. So I do 3 plus 4. I'm going to add some parentheses to make it clear. 3 plus 4 multiplied by 6. And now we're going to subtract minus 3. So it's minus 3. So this AST here, this abstract syntax tree here, represent exactly this. Can everyone see how this represents this here? Okay, so now in the first thing that we want to do is being able to show this tree, so I can display it on the string. On the screen, I mean. So how do we do this? We will map this structure into a rows tree. So into a multi-way tree. So we are going to do it once again, just like we did it before. Let's go to recursive, to Matreoshka. Let's go to kata again, and what's our recursive structure here? Remember that to get the recursive structure, we need to fix the expression, something. We need to do. We need to fix the pattern functor. So it's fix exprf, and you probably remember that I wrote a type synonym here. Type expr is fix of exprf. So here t is expr. Expression. F, can someone tell me what's base here? Sorry? Expression F, exactly, expression F, that's the base. If you look at the table that I gave, that was in the gist, you you can see that for expr is expr f. And we want to produce an A. We want to produce a tree. So we will replace all A's here with tree of a string. A tree of a string is a tree which has nodes that are strings, so we can show them. So this is why it's tree of string. And in here too, it will be tree of a string. So in order to produce a tree of a string, I need to write this algebra here. So when I actually wrote this, I had no idea how rows trees in Scala C worked, or how to convert my structure. I just decided, okay, I'm going to look at the types. I did exactly this. I was sitting at a coffee shop at Pearl Street, did exactly this, and came up with an implementation that works. And this is the beauty of recursion schemes. There's so much information on the types that you can just blindly substitute types in it, and you will get something that works. Okay, so we need to write this. Let's expand this type synonym. Can someone help me expand this type synonym here? This algebra expr f tree string.
Tree of string to x that of tree of string, right?
Exactly. So it's expr f of tree string. In this case, the recursive position will be a tree string. Remember, we made it polymorphic because we first had an integer, then we had a string. Now we have a tree in the recursive position. So we needed to make it polymorphic. Expr f string, and these go to tree string, which is the end result of what we want. So we need to write a function with this type, and we need to have a base. An implicit functor here on the base, which will be expr f. And I show you that we already wrote this too. So let's go back to linkedlist, to expr, to expression, and we are going to write this function. As always, we start with the non-recursive part of this structure. In this case, it's the literal. So we need to create a leaf. So we go to the literal, we need to create a leaf, we do i.shows to convert the integer. Since literal is always an integer, we will get tree leaf i.shows, okay. And we have this add f, and we're just going to add tags to it, like tree.node add. A stream, you can think, a stream is only a lazy list. You can replace mentally string to list, and it will work fine. I don't know why they made it a stream. I didn't understand when I say why it's stream, and then I pretended at least, and everything goes well. Same here, like add a stream lr, a stream lr, a stream lr. This L and R, this will be a tree, this will be a tree, this will be a tree. All of these will be trees. So when we are going to fold, we will start with the literal, then we will go to the rest of the constructors and go splicing the trees in there. So let's run this and see how, and the Scala C provides this nice draw tree function that will take a tree string and give us a string to print on the terminal. So let's execute this code and see where that gets us. Oh, yeah, I should have deleted that. Let's check out that. Yep. So now we have drawn our tree. This is exactly what we had before. We have an add that adds 3 to 4. So can someone tell me what would be the result of evaluating all of this, or evaluating this expression tree? First, we take the add. Yeah, go ahead.
What do you mean?
Like
3 plus 4?
Yeah, 3 plus 4 multiplied by 6 and subtract minus 3. So we have 3 plus 4, 7. 7 by 6. I didn't learn my timetables. 42. Yeah, we can actually do this programmatically, and we will do it here. But as always, we always start with show, since we want to be able to know what we are modifying and showing, what we're going to splice. So let's go to the next checkpoint, which is checkpoint 6. We are going to evaluate the tree. Okay, checkpoint 6. Checkpoint 6 will evaluate. Okay, so in order to evaluate this tree, it's pretty straightforward. You have a literal f. We start with a literal f, which is an integer. We need to go from x per f to integer. Our end value will be integer, an int. So we go case literal f, I. In the case it's a literal, it will be just I. If we are adding left and right, we just add, multiply, and subtract. And then just call kata on that, and it will give us back an integer. So let's execute this code. Yeah, and the evaluating tree is 45, which is adding 3 plus 4, then multiplying by 6, and subtracting minus 3, which is adding 3, of course, and we get 45. Now let's do something very similar that we did with map. We're going to make the A, the end result of the catamorphism, we will make it another, like the same expression. This will be a tree rewrite. This is like the very core of most compilers, and which is very similar to mapping. We will use the exact same steps. Okay, let's go to checkpoint 7, and we're going to transform this tree. Okay, so we're going to spice it up a bit by transforming this tree. Okay, so now we want to being able to give an expression to Matreoshka, to kata, and get back another expression, like something of the same type, just that we did with filter. Only that in this case it will be with expression. Let's go to Matreoshka for this. Let's delete this. And I shouldn't have changed the original one. Yes. Give me a second. Okay, so this should be 8. Okay. So we have a recursive structure here, which is expr, which is our tree, and we want to produce an expert too. We want to go from expression to expression. So let's work with the types again. Let's replace all A's with expression. I replaced the end A here. Let's replace the other one here. Can someone tell me what base is? Expression F, exactly. Expression F. We need a functor in expression F. Okay, so we need to write this algebra. So let's expand the algebra. And expr F, expr to expr. Okay, so we need to write this function in order to splice splice a tree, to rewrite a tree, to even to convert these into a different tree, like for rewriting an AST to compile in a compiler or something. We are going to write this algebra, which is exactly what we had here, algebra expr F to expr. So we pattern match on expr F, multiply F, left, right, and fix, since we need to produce this expr. We just need to fix the add F. So what we are doing here is replacing all multiplication in our tree with addition. And we can execute this, and we will show both trees. This is our original tree that evaluates to 45. This is our transformed tree, where the multiplication has been replaced with addition. So we have effectively rewritten an AST.
Question.
Go ahead.
So I'm thinking about like writing a compiler where you might want to change, say, distribution of multiplication over addition and expand that out. But you're at multiple levels of the tree there. Like if you wanted to say 3 times 4 plus 6 equals 3 times 4 plus 3 times 6.
Yeah, I don't think you.
Because like in a catamorphism, you're working with one level at a time, and to do a transformation like that, you have to look at multiple levels.
Yes, that's something we can do with an anamorphism, which I don't know if we will have time to cover, but there are, but examples are in the code, in the same repo. It's checkpoint 8, I think. I try to speed up so we can get into that part, so we can see how to transform an AST both recursively and co-recursively. This is the recursive in transformation of an AST. We will do the same thing, just co-recursively. Okay, next checkpoint 8. Yeah, this is co-transform tree. Checkpoint A. Okay, so now we have something different. We have, instead of having an algebra, we have a coalgebra. The coalgebra is exactly the same as an algebra, only switch it. So instead of going from expert f expert to expert, from expression f expression to expression, we go from expression to expression f expression. I will show you, and we will look at Matreoshka to do this do this again. Okay, so I will write the coalgebra type synonym here. Type, just so we have it as reference. Coalgebra of f of a type constructor, and A is A to FA. Okay, so this is just a type synonym. We just need to expand it. This is what they call an I think they call it as an initial coalgebra. I'm not familiar too much with the theory, so I'm not sure I can explain that. But in this case, we are able to look at the entire structure at once, just as you said. In this case, we are just going to do it for multiplication, like we are going to do the exact same thing. So, but first, let's look at the types. There is so much information in the types that not looking at them is losing information and even documentation. So let's look at the types. So instead of going to recursive, we are going to co-recursive. And we are going to use ANA in this case. As you can see here, co-transform uses ANA. I'm going to comment that because it's going to conflict. But now, okay. So, ANA is a little different to what we have. Instead of A being the end of being the result of the transformation of the recursive algorithm, in this case, A is the input for ANA. So, and T is the recursive structure. They usually call A a seed, but like the seed analogy doesn't make it very intuitive to me at all. Sorry? Someone say something?
Oh, I was just agreeing with that.
Oh yeah, no problem. Okay, so let's go to ANA. Okay, so we have an input. In our case, will be A. So let's replace A. We will pass to ANA. We will pass A. We will pass it a recursive structure. So we will pass it fix x per f. Base is the base of T. So we will expand that later. But what is T here? What do we want to produce in a transformation? Expression, right? So we will do a fixed expression. And always base is the base of T, is the base functor of T, is the pattern functor for T. So coalgebra, so what is the pattern functor for fix x per f? If you look at the gist, you can fix x per f is the recursive structure. The base is expression f. So we have this expression f here. We replace the a's here too to be fixed express. So effectively, the root of our the root, I mean, what they usually call the seed of the anamorphism, is a recursive structure. And this is something that took me a long time to understand when I first worked at Slam Data, that when you're transforming something corecursively, the seed, there's no seed like this. There is a seed, and the seed is a recursive structure. So in order to go from fixed express to express, coalgebraically, we need to write f coalgebra from xprf to fixed express. If we expand this type synonym here, we are no longer working with layers, with one layer at a time, as you said. We are now working with we are now working with entire recursive structure at once. Oh, wait, I confused myself. Yeah, we have fixed xpref, and this will, yeah, something like that. Okay, so now we can write this here. So now we are pattern matching on fix. We are pattern matching on the entire structure. So I could even go ahead and say I want to replace I want to rewrite all multiplication that have additions inside them. So I could pattern match here and add f and say left, right. Sorry? Oh, that's fixed. Yeah, good catch. There's always a fix in between the layers of the tree, because we need something in there in order to be able to define the fixed point. But let's keep it as it was, because this did the exact same thing of the recursive one, and I want to show it that it works exactly the same. Okay, so now we're doing the exact same thing we did before. We take this tree and we are going to co-transform it, like transform it coalgebraically. And now we can consider, like, we can transform multiple layers at once. And not only multiple layers, I can consider the entire tree at once and replace it with something else. This is the most interesting part in the Corecursion part of things. We also will. I will go very quickly to get to the annotations, which was in the title of this workshop, which is annotating a tree with cofree. Okay, this is a little bit more complicated. We are going to write a coalgebra to annotate a tree. So we want to go from an expression to a cofree of expression integer. So let's build some intuition first by looking at the result of this. Okay, this is the annotated tree. This annotated tree, all it does is annotates all the intermediate in results here. So add what's there, well, the intermediate, like the result of 3 is 3, of course, right? Of 4 is 4. Of adding 3 and 4 is 7. So we have this intermediate, like the result here. The intermediate, the result of the multiply, 42. And the subtract result, we have the final result, which is 45. We'll look at how this works. I think we have, oh, we're out of time now, so I just realized it. But it's very much the same. You just need to look at the types, look at the table that I gave you in the gist, and you can make everything match that way. After that, we will going. We can do these annotations are done corecursively too. Only that instead of unfolding over ourselves, we unfold over MT. So we end up with a cofree at the end. at the end, which give us this structure that is our AST annotated with intermediate in results. This is also very, very common in compilers, to take an AST and annotate some data on it. Okay, thank you very much for being here.